Jacob, floor is yours.
Well, thank you for the introduction. I'm Jacob Gottfried. I'm a PhD student at University of Wisconsin, and I'm here to talk about a project that we're doing in partnership with GTI Energy. And so we're talking about hydrogen natural gas blends. And the first question is, why do we actually care about these? Well, at least in the United States, we rely pretty heavily on natural gas as an energy source. And in the coming decades, we're expecting this reliance to not change dramatically. And so it's a little concerning because a lot of energy sectors are aiming to reduce their carbon impact. And so people are looking at ways to reduce the carbon impact of using natural gas. One such way is by blending hydrogen into that natural gas stream. Hydrogen, when it's burned, doesn't produce any carbon dioxide, so it has a lower greenhouse gas effect. And it's also historically been used as a home energy source back in the 1940s through 70s. The other benefit of using it is that when blended in typical fractions up to about 20% hydrogen, there's only minor changes needed to the existing natural gas infrastructure. And so utility companies see this as a promising near-term solution to reduce the climate impact of natural gas because it has a fairly low cost point in order to get into this green technology. But there are some complications in that there can be some variability in the actual concentration of hydrogen that reaches consumers, even if there's some good blending. This can come from a few ways. The first is at blending sites. Due to the use cycle of natural gas, there's very high fluctuations, and you may not be able to get appropriate blending in order to achieve a very constant product. But this can typically be solved through engineering controls. The larger side of the problem is that it's believed that there is a possibility of separation of hydrogen and natural gas due to the complex nature of the natural gas distribution system. And so it's important to be able to monitor the amount of hydrogen inside of the natural gas system at a varying set of points in order to ensure that there's a consistent blended product being delivered. And so because there are some concerns with this variability, there's a few possible issues that can pop up. The first comes down to a safety issue. Once you start blending in hydrogen, it does slightly alter the characteristics of this gas. And if you have rapid changes in the concentration, you can have very bad effects such as flashback due to improperly tuned equipment. And so in order to have equipment run safely, you're going to want to have some confidence in the amount of hydrogen that these systems are burning. The more important thing, or the other side of this, is that once you blend hydrogen into natural gas, you do change the energy value on a volumetric basis. And so in order to have this as a true commodity, you need to have an appropriate way to bill consumers based on the amount of energy you're providing them. Today, most utility companies charge consumers based on a energy basis, and they do this by actually measuring the amount of volume of gas a consumer uses and then convert that to energy. This gets a little bit muddled once you start adding in the effect that there could be a varying hydrogen concentration or a varying energy product being delivered to the consumer. And so because of these two effects, utility companies have said that they really want a sensor that is able to measure hydrogen directly and at a price point where this can be distributed around their distribution network in order to ensure that they are delivering a proper product to all of their users. And so that comes into the question of how is it measured? Well, as of today, there are commercial products that measure hydrogen blended into natural gas, but they typically have several drawbacks. Most commonly, the most common sensor used today are thermal conductivity sensors, which don't directly measure the hydrogen, and they're also going to be commonly restricted into the concentrations of hydrogen they can measure, typically only having a ability to measure anywhere between a 5% to 20 or 30%. And so we're looking at processes that don't have these same restrictions. For this work, we're looking at using vibrational Raman spectroscopy because it fills a lot of the goals that utility companies are looking for in a sensing technology. The way Raman scattering works is you can use any lasing wavelength, send it into a gas, liquid, or solid, and then when the photons interact with the molecules, they're going to experience a slight shift in energy. And this energy shift is directly related to the vibrational energy shifts inside of a molecule. And so by looking at the scattered light and measuring the relationship between the energy of the scattered photons and the incident laser light, you can create a spectra that gives details about the molecular structure of the gas. And so this is great because it allows for concentration measurements by looking at the ratios between different gases based on their relative intensities. But the downside of this technique is it's fairly weak, but there is a scaling to 1 over the laser's wavelength to the fourth. And so we're using recent kind of advancements in diode laser technology, using near ultraviolet lasers that can provide multi-watt output at very low costs in order to get a higher amount of signal with a fairly inexpensive package. And so for Raman scattering, the first kind of question is there going to be an ability to isolate the hydrogen feature, especially once it's going to be around things like natural gas, which have a very strong Raman scattering cross section. But luckily, hydrogen has a little trick up its sleeve in that its first vibrational energy shift is actually quite large compared to most molecules. And so it is over at 4,000 wave numbers, where typically methane is going to be around 3,000. And so this big jump allows us to isolate the hydrogen feature. This can be further done by just using appropriate polarization. And so when you look at the this spectra here, where this black is what you get when you look at atmospheric pressure hydrogen versus an overlay of natural gas in the same region, you can see that it's fairly well isolated. There is a small feature due to natural gas, but by just using a simple bandpass filter, you can isolate the hydrogen feature and then integrate the amount of signal that goes through that bandpass filter. And if you look at that integration versus the partial pressure of hydrogen, there's a near linear relationship. And so this allows us to use a very simple detector, which is just going to be a single photodiode that's based on silicon that can just measure the absolute intensity transmitted through this bandpass filter in order to measure the amount of hydrogen. And so using these ideas, we developed a sensor that is aiming to be a relatively compact and cost-conscious design, where we're taking a inexpensive diode laser that's capable of multi-watt output at 402 nanometers. This is sent through a dichroic filter into the gas using a lens sealed into a half-inch NPT fitting that can be put onto a natural gas line. Then the backscattered light is sent through a series of filters, and then it goes into a polarizing modulator filter, where this is a fairly simple device that's just a plastic polarizing film that is then rotated with a piezoelectric motor in order to allow us to measure both the polarization plane that is parallel to the laser's polarization, as well as the perpendicular plane. The light that then goes through this polarizing filter is sent through a bandpass filter to isolate the hydrogen feature, which is then directed onto a single element silicon photodiode in order to give us information about both polarization planes in a relatively compact time period. And so this is an example of what our sensor looks like today. It doesn't look like much yet because we're mostly relying on what you can do or buy for off-the-shelf mounting solutions. So it's a little bit large, but we do believe that in the next phase, we'll be able to miniaturize this device into a fairly compact form factor, something you could probably hold in your hand, which is about what you'd see from similar sensors on the market today. And so using this design, what we actually end up getting out of this sensor in the relatively raw data is a time-based signal of two polarization planes, where the in plane is going to contain the vibrational Raman scattering from the hydrogen, and then the out of plane is going to include things. This lower one is the perpendicular polarization, so it has a little bit of the Raman feature, as you can see at the 100% measurements. But this is mostly just due to leakage in the optics. The other things that are contained are things like fluorescence or competing optical signals, which are usually the major drawback from Raman spectroscopy. These things can easily overpower the main signal. And so by having this other feature, we can do effectively a subtraction of these two and isolate the feature that we actually want to get a stable output. And so when we use these two different polarization planes, you can get rid of things like if you see these are supposed to be flat, there's some kind of changing in the baseline. These would interfere with your signal, and they're definitely going to be over about the 1%. And so when you do a subtraction, you actually see that you end up getting fairly flat output from this. You can get rid of a lot of that temporally changing things. And so what this top figure is showing here is a test over the course of 48 hours where we have a series of mass flow controllers varying the hydrogen concentration of the gas going into the sensor. And that is that orange line, which is the prescribed concentrations. And then the blue is the output of the sensor, where it's currently operating at a time response of 30 seconds. This can be sped up to about 5 or 6 seconds, but that change is not really important as far as the use of the sensor. And so we've stuck with the 6 or the 30 seconds to match more or less what commercial products are doing right now, while still maintaining a fairly good output sensitivity, where our error over the course of 48-hour testing is going to be maintained below the error that we can achieve in our blending setup. And so this matches quite a few of the key parameters that utility companies have asked for in a sensor. This can achieve a less than 1% absolute error measurement, while also being able to achieve full-scale hydrogen measurements. Anything from a roughly 5% of an atmosphere can be measured all the way up to pure hydrogen at elevated pressures. And so this is a significant advancement over a lot of the other sensors that are out there on the market, which have a limited range in which they can measure. And then this also has no cross sensitivity to other gaseous species, which is a huge benefit, especially when you're looking at applications where the consumer really wants high confidence in how much hydrogen is actually within that gas. And so in conclusion, we've demonstrated that a Raman-based sensor can hit a lot of the key criteria that utility companies set out for a sensor for natural gas blending situations. We've also shown that a Raman-based sensor has strong potential for a commercializable product because it does outcompete a lot of the current sensors on the market for what they can achieve. But at this point, we do need to do quite a bit of future testing through things like temperature, environment, shock, and field testing to prove the validity of this approach. So with that, I'd like to open for questions. Thank you.